Greetings everybody. My name is Vivek Kasala and I am from Institute of Aeronautical College and I am a student of branch CSC of section D. Today I am here to present a tech talk on the topic generalization of Cayley-Hamilton theorem of multivariate rational matrices. Moving on to the next slide. Contents. So in total, this topic has a total of 6 subtopics. Now we are going to have a glance over all the six subtopics. So the first subtopic is Introduction of Generalization of Cayley-Hamilton Theorem of Multivariate Rational Matrices. And the second subtopic is Introduction to Cayley-Hamilton Theorem. And the third subtopic is What is Cayley-Hamilton Theorem? And now the fourth subtopic is Examples of Cayley-Hamilton Theorem. The fifth subtopic is what is the formula for Cayley-Hamilton theorem. Then the sixth subtopic is this theorem applicable for all types of matrices? Moving on to the next slide. Now we are going to have a detailed explanation on over all the subtopics which are given in the contents. So now moving on to the next slide. The first subtopic is Introduction of Generalization of Cayley-Hamilton Theorem of Multivariate Rational Matrices. Introduction. The classical Cayley-Hamilton theorem says that every square matrix satisfies its own characteristic equation. The Cayley-Hamilton theorem has been extended to rectangular matrices, block matrices, pairs of commuting matrices, and standard and singular two-dimensional linear system. So in short, this slide can be explained as that the Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. And the next point says that the rectangular matrices, block matrices, pairs of commuting matrices, and standard and singular two-dimensional linear systems are all applicable for Cayley-Hamilton theorem. Moving to the next slide. Now this is the continuation of the first subtopic, Introduction of Generalization of Cayley-Hamilton Theorem of Multivariate Rational Matrices. Here the first point is the Cayley-Hamilton Theorem has been extended to n-dimensional systems. And the second point is an extension of the Cayley-Hamilton Theorem for 2D continuous discrete time linear systems has been given in. Moving on to the next slide. Now this is the continuation of the first subtopic, Introduction of Generalization of Cayley-Hamilton Theorem of Multivariate Rational Matrices. Here the first point is the Cayley-Hamilton Theorem and its generalizations have been used in control systems and also automation and control in electronics and circuit theory, time systems with delays, and singular 2D linear systems, 2D continuous discrete linear systems, and automation and electronics, electrotechniques, etc. So in simple and short words, it can be said that in this slide, the control system and also automation and control in electronics and circuit theory, time system with delays, singular 2D linear system, 2D continuous discrete linear systems, automation and electrotechniques make use of Cayley-Hamilton theorem and its generalizations. Moving on to the next slide. It is the continuation of the first subtopic, introduction of generalization of Cayley-Hamilton theorem of multivariate rational matrices. In this slide, an overview of generalization of Cayley-Hamilton theorem is presented. The linear polynomial matrix A minus x into the identity matrix, which I denotes the identity matrix of det of A minus x into identity matrix in the classical Cayley-Hamilton theorem is replaced by the general polynomial matrix. Here the general polynomial matrix is given as f of x is equal to a naught plus a1 into x plus, and it keeps on going and keeps on going, adding up till it reaches a n into x to the power of n. So in simple and short words, it can be said that in this slide, a brief overview of Cayley-Hamilton theorem and its generalization is given. The linear polynomial matrix A minus xi of that A minus x into the iterative matrix in the classical Cayley-Hamilton theorem is replaced by the general polynomial matrix, which is f of x is equal to a naught plus a1x plus it keeps on going until adding until it reaches a n into x to the power of n. Moving on to the next slide. Now we are moving on to the second subtopic, introduction to Cayley-Hamilton theorem. In linear algebra, the Cayley-Hamilton theorem, termed after the mathematicians Arthur Cayley and William Rowan Hamilton, says that every square matrix over a commutative ring, for instance, the real or complex field, satisfies its own characteristic equation. In simple and short words, this can be explained as the theorem, Cayley-Hamilton theorem is named as Cayley-Hamilton theorem, as it is taken from the names Arthur Cayley and William Rowan Hamilton. So again, Cayley-Hamilton theorem can be explained as every square matrix over a commutative ring, where commutative ring is a ring in which multiplication is commutative, satisfies its own characteristic equation. Moving on to the next slide. Here it is the continuation of the second subtopic, introduction to Cayley-Hamilton theorem. If A is provided has n into n matrix and In is n into an identity matrix, then the distinctive polynomial of A is articulated as P of x is equal to det of x into the identity matrix minus the matrix A. So in short and easy words, it can be in this slide, it is given that if A is a n into n matrix and I is a n into n identity matrix, then the distinctive polynomial of A is given as P of x is equal to det of x into the identity matrix minus the matrix A. Moving on to the next slide. It is the continuation of second subtopic, introduction to Cayley-Hamilton theorem, where the determinant operation is det, and for the scalar element of the base ring, and the variable is taken as x. So it is referring to the previous equation given here. In this equation, det is the determinant operation, and x is taken as some variable. Moving on to the next slide. Now this is the continuation of the second subtopic, introduction to Cayley-Hamilton theorem. Has the entries of the matrix or linear or constant polynomials in X, the determinant is also an nth order monic polynomial in X. Now moving on to the next slide. Now moving on to the third subtopic, what is Cayley-Hamilton theorem? The Cayley-Hamilton theorem states that substituting the matrix A for x in polynomial, P of x is equal to det of x into the identity matrix, where the identity matrix is of n into n size, minus the matrix A results in the zero matrices, such as P of A is equal to 0. And Cayley-Hamilton theorem also states that n into n matrix A is demolished by its characteristic polynomial det of t into the identity matrix minus of A, which is molic polynomial of degree n. So in simple and short words, it can be said that Cayley-Hamilton theorem states every square matrix satisfies its own characteristic equation. And in the second point, Cayley-Hamilton theorem also states that n into n matrix A is demolished by its characteristic polynomial that of t into identity matrix minus matrix A, where t is here a variable, is the sum variable, which is a monic polynomial of degree n. Moving on to the next slide. What is moving on to the third subtopic, what is Cayley-Hamilton theorem, which is its continuation. The powers of A found by substitution from powers of X are defined by recurrent matrix multiplication. The constant term of P of X provides a multiple of the power A naught, A into the power 0, where power is described as the identity matrix. In simple and short words, it can be explained as here it is given that the power of A, which are found by the substitution of powers of X, are defined by recurrent matrix multiplication. So the constant term of P of X provides a multiple of the power A to the power 0, where power is described as identity matrix. Now moving on to the next slide. Continuation of the third subtopic, what is Cayley-Hamilton theorem? The theorem allows A to the power of n to be articulated as a linear combination of lower matrix powers of A. The second point states that if the ring is a field, the Cayley-Hamilton theorem is equal to the declaration that the smallest polynomial of a square matrix divided by its characteristic polynomial. In simple and short words, it can be explained as the Cayley-Hamilton theorem allows A to the power of n to be taken as a linear combination of the lower matrix powers of A. And in the next point, it is given that the ring is a field where the Cayley-Hamilton theorem is equal to the declaration to the smallest polynomial of a square matrix divided by its characteristic polynomial. Now moving on to the next slide. Now moving on to the fourth subtopic, example of Cayley-Hamilton theorem. The first example of Cayley-Hamilton theorem here is given for 1 to 1 matrix. For 1 into 1 matrix A, for capital A, the characteristic polynomial is given by P of gamma is equal to gamma minus A into P of gamma is equal to gamma minus A. And so P of A is equal to the A minus the matrix or the square matrix of 1 into 1 size is equal to 0 is obvious. Now moving on to the next slide. It is the continuation of the examples of Cayley-Hamilton theorem for 1 into 1 matrix. As a concrete example, let A is equal to be a 2 into 2 matrix where the first row has elements 1 and 2 and the second row has elements 3 and 4. Then in the second point, it is given that P of gamma is equal to det of gamma into identity matrix, which is of size 2 into 2, minus of minus square matrix A is equal to that of a matrix where it is a 2 into 2 matrix which has elements gamma minus 1 and minus 2 in the first row, and has elements minus 3 and gamma minus 4 in the second row, which is equal to the my whole gamma which is equal to the whole multiplication of gamma minus 1 into gamma minus 4, and minus of minus 2, and where the minus 2 is multiplied with minus 3 is equal to gamma square minus 5 gamma minus 2. Now continuing in the third point, the Cayley-Hamilton claims that if we define P of x is equal to x square minus 5x minus 2 into the identity matrix, where the identity matrix is of size 2 into 2. Now moving on to the next slide. Um, Referring to the previous slide, then P of A becomes P of A is equal to A square minus 5A minus 2 into the I2, which is I2 where I2 is the identity matrix, is equal to a zero matrix of size 2 into 2. In the next point, going to the next point, we can verify this result by computation. So by verifying this result by computation, A square minus 5A minus 2 into the identity matrix of size 2 into 2 is equal to a matrix which is equal to a square matrix which has 7 and 10 elements has in the first row and 15 and 22 two elements in the second row, and is of the size 2 into 2 minus of another matrix which has elements in the first row as 5 and 10 and has elements 15 and 20 in the second row, minus of another square matrix of size 2 into 2 which has elements 2 and 0 in the first row and other two elements 0 and 2 in the second row. And after this this whole equation is equal to a zero matrix where of size 2 into 2. Moving on to the next slide. Referring to the previous slide that we have discussed, for the example of a Cayley-Hamilton theorem for 2 into 2 matrix, continuing for a generic 2 into 2 matrix, A is equal to capital A is equal to a square matrix of size 2 into 2, where has its elements in the first row has A and B, and the second row has elements C and D. Now the next point is the resultant polynomial is given by P of gamma is equal to gamma square minus of gamma into whole into the multiplication of A plus D plus AD minus BC. Moving to the third point. So the Cayley-Hamilton theorem states that P of A is equal to A square minus of A into A into multiplication of A plus D plus AD minus BC to the multiplication of identity matrix of size 2 into 2 is equal to a zero matrix of size 2 into 2. Now moving to the fourth point. It is always the case which is evident by working out on A square. Now moving on to the next slide. What is the Cayley-Hamilton theorem in short, which is summarizing or recapping what is Cayley-Hamilton theorem. As per Cayley-Hamilton theorem, all the square matrix satisfies its own characteristic equation over a commutative ring of real or complex field. So now moving on to the next slide, or the next subtopic, which is the fifth subtopic. What is the formula for Cayley-Hamilton theorem? So if A is provided as n into n matrix, and I is the n into n identity matrix, and x is any variable, then the distinctive polynomial of A is articulated as P of x is equal to det of x into the identity matrix minus of the square matrix of A. Now moving on to the next subtopic, the sixth subtopic. Is this theorem applicable for all types of matrices? Yes, no, but the theorem is only applicable for square matrices. So in short words, it can be said that the theorem, the Cayley-Hamilton theorem, is not applicable for all kinds of matrices. It is only applicable for only square matrices. So I really hope you guys have gained valuable information and knowledge through my deep and thorough explanation of my tech talk on the topic generalization of Cayley-Hamilton theorem of multivariate rational matrices. Thank you.